Thank you. So thanks very much for the introduction from Paul. He's actually led me into exactly what I want to talk about, which is what we can learn from the past as we look to the future. So I'm actually going to go further back than Paul did. I want to take you back all the way to the 1800s. So in 1889, there was a pandemic that was called the Russian flu. And that was actually before any respiratory viruses had been discovered. The first respiratory virus discovered was flu, but it wasn't discovered until 1933. And so quite possibly this pandemic was not caused by flu, but by a different virus. And there's a camp out there now that are saying that this pandemic may actually have been caused by a coronavirus. So in this pandemic, around 1 million people died when the global population was around a fifth the size as it was now. And the respiratory symptoms were typical. So we had respiratory symptoms and GI, but then there's some symptoms as well that were really reminiscent of what's happening with COVID today. So people having a loss of sense of smell and taste, neurological complications, and around 1 in 10 people developing a long COVID-like syndrome, which is very oddly reminiscent of what's happening right now. And the scientific evidence supporting what the origins of this outbreak were are split. So serologically, it looks as though the evidence there supports it was an influenza pandemic. But molecular clock modeling predicts the emergence of a human coronavirus called OC43, one of the endemic coronaviruses today. It predicts that it emerged at pretty much exactly when this pandemic occurred. So the journey that I want to take you on today is going under the hypothesis that this pandemic was caused by OC43. And what I want to do is fast forward 120 years to see what happened in that potential intervening period between the emergence and the endemicity of human coronavirus, or OC43 as we understand it today. And I'm going to make a huge faux pas in this presentation because I'm going to present some work that we already published, and not just work that we already published, but we published in 2010 in relative obscurity when I was doing my PhD in the lab of Peter Simmons at Edinburgh University at the time. He's now based in Oxford. And Kate Templeton, who's a clinical virologist at Edinburgh University. And what we did was screened thousands of respiratory samples for the 4 endemic human coronaviruses, 229E, HKU1, NL63, and OC43. So you can see these represented phylogenetically here. So we've got the 4 endemic human coronaviruses indicated in orange at the bottom of the phylogenetic tree, and the other coronaviruses that have spilt over into humans indicated in red. So the inferences that I want to make about the journey that OC43 has made link very closely with the other endemic coronaviruses as well, and how much we can infer about what the future holds for SARS-CoV-2. It has to be taken with a pinch of salt because SARS-CoV-2 is phylogenetically disparate from these, but at the same time, it's not so distant that the history of these viruses can be lent to what the future may hold for SARS-CoV-2. So what we actually did was screened nearly 13,000 respiratory samples submitted to the diagnostic unit at Edinburgh Infirmary for the 4 human coronaviruses. So we collected samples between 2006 and 2009 over a 3-year period. On the right-hand figure, you can see the representation of the age groups that these samples were taken from. So these were predominantly taken from infants and young children. As you can see, we've got very narrow, just put my laser pointer on. We've got very narrow age ranges here. And then up towards the end, we've got older age groups as well. So we've got a good age distribution. The samples were collected from all kinds of hospital and primary care settings, so accident and emergency, general practice, high dependency units, intensive therapy units, mainly inpatient samples, also neonatal units, and some outpatients, specific subset of which were respiratory outpatients. And these samples were taken from people with a range of clinical presentations. So we did have lower and upper respiratory tract infections reported, but most of these samples actually came from other origins as well. So we had immunocompromised patients, patients with chronic respiratory infections who were being surveyed. Other clinical presentations that could be attributed to a respiratory virus, so for example, gastrointestinal systems, fever, meningitis, and plenty of samples had no attributable clinical data. The samples that we were screening came from mainly nasopharyngeal origin, but we also had samples from other parts of the respiratory tract as well. So the bronchi, the trachea, and nasal samples as well. So here you see the frequency of detection of all the different viruses. So we've got the 7 viruses that were included in routine diagnostic screening at that time. So we've got adenovirus, flu A and B, paraflu 1, 2, 3, and RSV. And you can see in the 13,000 samples how often these viruses were detected, indicated in boldface. Mixed infections are acknowledged in the not boldface numbers in this table. And then we have the detection of the 4 endemic human coronaviruses. So what you can see from this table are these 4 viruses are actually detected really quite infrequently. And the point of this, this project was to determine whether these 4 viruses should be included in routine diagnostic screening. And based on this data, it was decided that that was not an economically viable way forward. So the coronaviruses, the endemic coronaviruses in themselves, not causing a huge amount of disease at first glance. Looking at the data in a bit more detail, we saw that the 4 human coronaviruses were detected most frequently in infants and young children. They are detected in older adults as well, but mainly in infants and young children. So those infections are happening early in life. We also studied the seasonality of these viruses, and what you can see is that these are very much winter into spring type viruses, occurring mainly in February and March. And we did potentially see some epidemiologic interference between the beta coronaviruses. So here in the first respiratory season, we saw a predominance of OC43, and then that switched to HKU1 in the next respiratory season, and then it went back to OC43. And the other thing to note from this figure is that we did see very strong evidence of cross-circulation of influenza and coronaviruses. So that's something that's a concern this coming winter. When we looked at the clinical presentations that were associated with the 4 different seasonal coronaviruses, all of them, with the exception of 229E, were found in patients with lower or upper respiratory tract symptoms, but they were not particularly detected at a frequency as simple infections any higher than they were as mixed infections, indicating that we could not attribute any lower or upper respiratory tract presentations to these viruses specifically. And if we look at the detection frequencies of coronaviruses in lower and upper respiratory tract infection patients, you can see the detection frequencies are very low, and they're not much lower in patients with no respiratory presentations. So there are very minor causes of these respiratory presentations in patients who are requiring respiratory sampling. So now, given this information that I presented today, we can consider what happens next. If we're considering this journey that OC43 may have made from emergence in 1889, potentially to the endemic and not particularly disease-worthy virus that it is today, we can ask whether SARS-CoV-2 is, firstly, is it going to become seasonal? Given what we've seen for the other coronaviruses, that does seem likely. Will the epidemiology be influenced by other beta coronaviruses, as we've seen for HKU1 and OC43? That's really difficult to say because SARS-CoV-2 is phylogenetically disparate, but potentially there will be some epidemiologic interference there. And will SARS-CoV-2 reduce in clinical severity to more mirror the endemic coronaviruses? That's something that I've been wrong about before, so I'm not going to speculate on that. And finally, when will this pandemic be over? Well, the 1889 pandemic had outbreaks recognised associated with that for around 6 years, but that was at a time when global travel was a lot less and when we didn't have vaccines. So hopefully it won't quite drag on as long as that. So that's me. Thank you very much for your attention.